Okay, welcome to the Autumn 1 Week 6 exam correction video on the rate of reaction exam. So the first question tells us that we already have the setup to investigate the rate of reaction between magnesium and dilute hydrochloric acid. And we can see the equipment that's going to be used. So we see we've got a gas syringe already connected with a bung to a conical flask full of magnesium and dilute hydrochloric acid. So the question asks us to outline a plan to investigate how the rate of this reaction changed when the concentration of the hydrochloric acid was changed. So we've got two variables here. The rate of reaction is what we want to actually measure, so that's going to be the dependent variable. And when we change the concentration of hydrochloric acid, so that's going to be our independent variable. And what we need to do is describe how we would do the investigation and the measurements we would make. So that's crucial. We need to actually state what measurements we are going to make and how you would make it a fair test. When we see that phrase, fair test, that means we need to talk about control variables, right, which are the variables that we need to keep the same during the experiment. And also pay close attention to this, you do not need to write about safety precautions. So you will get no marks for writing about things that you need to do to keep safe. So what we're really interested in are the measurements that we need to make and the control variables. So turn over the page. Let's start answering this question. Okay, so the very first thing we need to say is how are we actually going to carry out this experiment? And the very first thing we need to do is remove the bung and add magnesium to the hydrochloric acid. And that first statement will actually get you the first mark because it makes it really clear what are you actually going to do. Now the second mark is to then say, well, how are we going to keep track of the rate of reaction? How are we going to keep track of our dependent variable? We're going to use a timer, so you need to say that you're going to start the timer, and that's the second mark. Then our third mark is for about how are we going to actually measure the amount of gas that's being given off. So we are going to use the gas syringe to measure the volume of gas produced. And what's really important here is we can't just leave it at that. We need to say the volume of gas that's produced, and we need to say a time period. So you could just say at fixed intervals, or you could be more specific and say maybe every 30 seconds. But you must mention checking the volume of gas produced at a particular amount of time. Otherwise you can't get that third mark. Now, mark number 4 is to show that we understand that we need to then try different concentrations. So that simply means we need to say, repeat the experiment with different concentrations of hydrochloric acid. So those first 4 bullet points will get us the first 4 marks on what measurements we're going to make and how we're going to do it. Now the next 2 marks come from talking about control variables. So the first control variable that we could mention is that we are going to use the same volume of acid each time. Okay, so that's one possible option. Another possible option is to keep the acid at the same starting temperature. And we've still got maybe one more other control variable we could use, which is to say use the same mass of magnesium each time. So to get the 5th and the 6th mark, you need to have said two of these three things. Okay, moving on to 1b. So we actually get to see the results from one of these experiments, and we're asked what is the volume of gas that's been collected. So to figure this out, we need to look at the scale, and we can see there's 5 and then 10 here, and then in between we've got some markings. So that's 5, that's 6, 7, 8, 9, and that's 10. And the gas syringe is about halfway between 6 and 7, which means the only sensible option here is 6.5. Okay, over the page. Okay, so here we've got figure number 3, shows the student's results for 1 concentration of hydrochloric acid. And then the table below shows the results when the concentration was 2 times greater than the results on figure 3. So we've got another table, and it asks us to plot the results in the table above on the grid in figure 3. So I'll zoom out so we can see both the graph and the results table, or as much of both as possible. And you might be able to see I've already plotted these points, but just to show you how I did this, first thing is to kind of have a look at the scales, and we can see down here the x-axis, we start with 0, we have 10 small boxes to get to 10, which means that one box is equivalent to 1 second. Now up here we've got our volume of gas produced, and again we've got 10 boxes, but we've gone from 0 to 20. So that means that each small box vertically is worth 2 centimeters cubed. So my first point is actually just 0, 0, and it is a good idea just to show a plot point there to show that you know that one should be plotted. Then at 10 seconds we've got 35. So 10 seconds easy to find. That right there, 5 boxes up is 30. That's 32, 34, 36. So it's got to be halfway between 34 and 36. So 35. Then 15 seconds and 52. So 15, 5 boxes along. And then if we go 5 boxes up, there's 50. And then 52. Then 20 seconds gives us 80 centimeters cubed. So 20 is easy to find, and 80 is also pretty easy to find. We plot that point. And the last one is 30 seconds, giving us 87 centimeters cubed. So again, 30 is easy to find. We go up to 80, that's 82, 84, 86, that's 88, so it's got to be in between. So we get 87. And if you plotted all those points correctly, you would get 2 marks. The third mark says we need to draw a line of best fit. We need to draw a line of best fit. So here we look at the points and it's not very clear what we should do. So you could look at them and think maybe we should draw a curve. But if we look at the data that's already been plotted, we see the other one was plotted as a straight line. So it would make sense to try and plot this one as a straight line. And although maybe one of the points won't quite fit, we are still going to draw a straight line starting from 0, 0. And the most sensible thing to do is to try and draw it so that our line of best fit gets as close as possible to these 2 points. We also could have tried to draw it a bit like this so that that point comes out as an anomaly, but I think it makes more sense to try and draw it so that our line of best fit goes between those 2 points near the top. So something like that. And that would get you the 3rd mark. Okay, turning over. Last question on this part. Give one conclusion about how the rate of reaction changed when the concentration of hydrochloric acid changed. So, if we turn back, right, we can see from this graph that this line, which is much steeper than this one, this was when we had twice the concentration. So this is 2 times the concentration. So this line is representing double the concentration as the first one, and we can see that we're getting volume of gas being produced faster. The line is steeper. And because we can see that line is steeper, that should tell us that the rate of the reaction is steeper. More gas being produced in a smaller amount of time. So, for this 1 mark, our conclusion has got to be that when the concentration of acid increased, the rate of reaction increased. Now, to get the mark, and this is really important, you need to say both of these things, that when the concentration was increased, then the rate of reaction was increased. If you just wrote the rate of reaction increased, you would not get the mark, because the question isn't asking you about what happens when the concentration increased. It just says what happens when it's changed. So you need to actually say what the full relationship is. So when the concentration increased, the rate of reaction increased. Okay, question number 2. So again, another experimental setup. And in this one, we've got a student investigating the rate of reaction between calcium carbonate, so some marble chips, and hydrochloric acid. And we see the equipment that they're using. So this time, no gas syringe. This time what we're doing is using an upside down measuring cylinder filled with water, and as the gas comes through, it's pushed the water level down, and this right here is going to be a measurement of how much gas, how much carbon dioxide is being produced. So they've recorded the volume every 5 seconds, and they repeated the experiment using hydrochloric acid at different temperatures. So they've been changing the temperature and recording the volume of gas. So we've also got an equation for the reaction, and then it says they plotted the results at 20 degrees and 40 degrees Celsius. So let's have a look at what they got. Okay, so a couple of key things we can see already from this graph, which is the 40-degree line. We can see that it is steeper than the 20-degree line, and also it levels out faster. Those are 2 indications that the 40 degrees is a higher rate of reaction. So the first, that it's a steeper line, which means the gas is we're getting the same amount of gas in a shorter amount of time. So that's indication number 1. And then indication number 2, that it's a quicker rate of reaction, is that the line kind of goes horizontal quicker. And when the line goes horizontal, that's telling us the reaction is finished. So for 40 degrees Celsius, the reaction has finished sooner than for 20 degrees. Now let's have a look at the questions. So, one conclusion the student could make about the effect of temperature on the rate of reaction. So we already kind of figured this one out, and the conclusion will be that the rate of reaction is greater at 40 degrees Celsius. You could phrase that differently. You could say that the higher the temperature, the greater the rate of reaction. But because we've only got 20 and 40 degrees, it's probably safer just to make that statement. Now, part 2, give one reason why the student can make that conclusion. Well, we've actually already got the 2 possible reasons we could give up here. So you could either say that the 40 degrees Celsius line is steeper, or you could say that the 40 degrees Celsius line becomes horizontal more quickly. Both of those are absolutely sensible reasons why we know 40 degrees is a faster rate of reaction. Okay, the third part of the question gives us a bit of data and we need to do a calculation with it. So we've got the students collected 30 centimeters cubed. There's our quantity of product formed, and after 15 seconds. So we need to find the average rate of reaction. Okay, so I've already said it, the kind of quantity of product, you can call it QP, is 30 centimeters cubed, and the time here is 15 seconds. And we're asked to find the average rate of reaction. That could also be the mean rate of reaction. And to find that, for short, M or OR, the mean rate of reaction is going to be the quantity of the product divided by the time, which is 30 divided by 15, which is equal to 2. And so our rate of reaction, or our average rate of reaction, is just 2 centimeters cubed per second. Okay, the second part of the question. So the student then investigated how the surface area of marble chips affected the rate of reaction. So which 2 variables should be kept constant? So we need to have a look through and see what do we need to keep the same so that it doesn't have an effect on the rate of reaction. Okay, so the amount of water in the trough. So just going back to the diagram. Okay, so how much water we put in here. Now for the moment, maybe that seems like something we should keep the same. So let's keep that in mind as a possible option. Then the concentration of the acid. Now we know immediately if we change concentration, it's going to change the rate of reaction. And we want to investigate surface area. So immediately we've got to make sure that that's one we do keep the same. Now the mass of the marble chips. Okay, that's another interesting one that maybe we should think about keeping the same, because if we use different amounts of marble chips each time, we might end up with different amounts of gas being produced, which is maybe something we don't want. Now the size of the marble chips, so that is definitely something we actually want to change, because different size marble chips will have different surface areas, so that's definitely, we don't want to change that. And then the volume of the measuring cylinder. So that again maybe seems like a sensible suggestion, that maybe we want to use the same one each time. So we've got 3 possibilities that we could be our second option. Maybe the amount of water, maybe the mass of marble chips, and maybe the volume. So the correct answer here is the mass of the marble chips. The other 2 we don't have to keep the same, because the other 2, what they are going to do is, if we do keep the same, it will be helpful, because we'll always start with a full measuring cylinder of the same size, and when the gas comes through it will push the water down. But even if the second time round we started with the water down at this level, all that's important is how much gas has been produced. So as long as we just read what the level was at the start and then read where it gets to at the end, we'd still be able to measure the volume of gas perfectly correctly. Whereas if we change the mass of the marble chips, then we might end up with different amounts of gas being produced, different amounts of carbon dioxide, and that could make the results hard to interpret. So that's why we want to keep the mass the same. Okay, the next part of the question Explain in terms of particles and collisions the effect that increasing the surface area of the marble chips has on the rate of reaction. So, surface area is the thing that's being changed, and what effect does it have on rate of reaction? Now, it's really important to, when you get a question like this, to always look at how many marks it's worth, because that tells you how many things you are going to need to say, how many points you're going to need to make. Now, it does explicitly mention particles and collisions, so we are going to have to use that language in our answer. So, when we change the surface area, when we increase the surface area, the first key thing that does is it exposes more reactant particles. And if this was a 3 or 4 mark question, I would definitely include that. But it only says the effect that it has, and in terms of particles and collisions. So if there are more particles of the reactant exposed, then what that's going to mean in terms of collisions is that there are a greater number, or let's phrase it differently, that there are going to be more frequent, and really importantly, more frequent successful, we need to say more frequent successful collisions of particles. So more frequent successful collisions. We must have the word frequent, we also must have the word successful to indicate that they're actually breaking bonds in those collisions. And then the second point here, what effect is that going to have on the rate of reaction? It will increase the rate of reaction. Okay, then we're on to the final part of this question, 2C. So calcium carbonate is a catalyst for the industrial production of biodiesel. Give one reason why using a catalyst reduces costs. So there's plenty of reasons we could give. So one is simply that a catalyst will increase the rate of reaction, and if the reaction's happening faster, then that's going to mean it's going to cost less money. Other possible options is that the catalyst will reduce the energy required, so we'll need to supply less energy for the reaction, which is going to keep the cost down. You could also have said that a lower temperature can be used. And there's one more, which is, this is going to reduce costs because the catalyst is not used up. So you can use it over and over again. So one of those will get you that mark. Okay, we're on to the final question, number 3. Again, about an experiment. So this one, about an experiment we talked about in lessons, which is when we react sodium thiosulfate and dilute hydrochloric acid, and you look through the reactants from above, and underneath you've got a cross, and the reactants will start to react and produce a cloudy substance. And the way of measuring the rate of reaction is to measure how long does it take for the cross to become hard to see. And so the table underneath shows how long that took at different temperatures. So we're seeing we've got increasing temperature, and unsurprisingly the time that's taken is going down. So let's see what we're asked to do. Okay, so first is to plot the data from the table on figure 2, and then to draw a line of best fit. So you can see I have already plotted the points again, and let's just to make sure we know where we're going to plot the points, you should look at the scale. So from 0 to 10 is 5 small boxes, which means each small box is worth 2 degrees Celsius. And again, with time from 0 to 10, 5 small boxes, so each small box is worth 2 seconds. So the first point up here is the point 25 degrees, and the time is 89 seconds. So 25 degrees is going to be dead in the middle between 20 and 30, and then that's 89, just above is, sorry, that's 88, just above is 90, so that's where we get 89. And then the next point we're plotting is 32 temperature and 62 seconds. So 32 is going to be just one small box along, and then 62 just one small box above the 60 line, so that's where that one is. And then 44 degrees Celsius and 33 seconds. So 44, we need to go 2 boxes along from 40, and then 33 seconds, there's 30 there, 32, 34, so it's going to be halfway in between. Next point is 55 degrees Celsius and 17 seconds. So 55, there's 52, 54, so 55 is halfway up, and 17 seconds, so there's our line for 10, 12, 14, 16, 18, so it's halfway in between there. 3 more points, so 64 degrees, 8 seconds, so 64, 2 boxes along from 60, 8 seconds, so 2, 4, 6, and 8. And then we've got 2 more points to get. Next one is 75 degrees and 5 seconds. So 75 is going to be halfway along here, so 72, 74, 75, and then that's 2, 4, and 5 is going to be just in between before the next box. And then finally we have the point 85 degrees and 4 seconds. So 85, there's 80, 82, 84, 85, and then 2 and 4 seconds. So if you plotted all the points correctly, then you would get 2 marks. If you made more than 2 mistakes, you only get 1. And the third mark here is for drawing a line of best fit. Now, looking at the points, it's quite obvious that it's starting to get more and more horizontal. So we wouldn't want to draw a straight line of best fit here. We actually want to draw a bit of a curve. All right, so we should try and do this in one smooth motion. I'm going to do my best here. So, it's getting a bit wobbly. Okay, and one smooth motion through the points. Not so smooth, but we should have a curve a little bit like that, probably a little bit smoother than mine. And if you've got a curve like that, you will get your 3 marks. Part B of the question says describe the trend in figure 2, and it says use values from figure 2. So we need to quote some data that we can get from our curve or even from the table. Now, most obviously, first of all, let's actually just say what we can see is the relationship between the variables. And we can see when the temperature increases, the time in seconds decreases. So let's make sure that's our very, very first statement. So as temperature increases, the time decreases. Okay, so that's going to be point number 1. Then, because it says use values, we should give some examples. So we could say, for example, and easiest thing is actually to use some data from the table. So at 25 degrees Celsius, the time was 89 seconds. And we can't just stop there. We have to illustrate the trend we've pointed out, which means we need to give a second point. So, so let's pick one that was later on, at 55 degrees Celsius, the time was 17 seconds. Now that second point there, that's now really illustrating the data is agreeing with our first statement. But hold on, this is a 3-mark question, which means we should also make a comment about the fact that it's not just a straight line, but actually it starts pretty steep and then starts to curve off. So the 3rd mark and the 3rd point you should make is that at higher temperatures, the decrease in time is smaller. Now, what I mean by that is when we change from 25 to, let's say, 32, we got a big drop. We went from 89 all the way down to 62. But when we go from 64 to 75, we're only changing by 3. So we're getting a much smaller drop. And that's what that 3rd statement is saying. So at higher temperatures, the decrease in time is smaller. So you need some statement like that to get the 3rd mark. Okay, we're on to the final question. Oh, sorry, no, 2 more to do actually. And this one, we are given some data from a student who investigated the effect of concentration on the time taken for the reaction. So this time they've changed the concentration, and here we see the results. So similar thing, we're getting a curve, and we get some instructions. Draw a tangent to the curve at 0.20 moles per decimeter cubed. So that's our instruction, 0.20, and then calculate the gradient of the tangent at that point, and finally give the unit. Okay, you can see that I have already drawn my tangent. So the way that I did this is first I identified the point that I needed. So 0.20 is right here. That's the point we need to draw the tangent at. And the way I figured out where to draw the tangent is I tried to bring my ruler along to that point, and I kept moving it along until all I could see was just the bit of the point I've drawn, and that the curve is now all underneath my ruler. And that's where I drew my tangent. Okay. Now, you might have drawn it slightly different, and that will lead to a different final answer, but let's now use this to calculate the gradient. So, calculating the gradient, we need to now use the tangent as a hypotenuse and draw a right angled triangle so that we can do the rise divided by the run. So you should try and make your triangle as large as possible, because that's going to make the calculation more accurate and also makes it easier to do. So I can see from my triangle here, the rise is actually 40, and the run across here is 0.40. Now, something we do need to be careful of is this is downward sloping, which actually is going to tell us that the gradient of this should be negative. Now, we're going to add that in at the end. So for the moment, to get the gradient, we're going to use that formula. It's equal to the rise over the run. And that is equal to, from my triangle, 40 divided by 0.40. Now, when we do 40 divided by 0.40, you get 100. So like I said before, this actually is a downward sloping line, which means that actually the gradient is negative, and it's actually negative 100. Now, if you put 100 or negative 100, both answers will be accepted. It's probably better to say minus 100, because that really is technically the gradient, but if you left out the minus, you'd still get the mark. And the final thing is to figure out the unit, and that is not simple from this graph. So to find the unit, when we find the gradient, you need to use the units from the axes. So our y-axis was in seconds, our x-axis is in moles per decimeter cubed. And when we found the gradient, we did the value from the y-axis divided by the value from the x-axis. And the unit takes those, the final unit will take those units. So we take the seconds, and then because we divided by the y-axis, it's going to be seconds per mole per decimeter cubed. So that is to get the fourth mark, is seconds per mole per decimeter cubed. And that was very, very tricky. So really well done if you managed to get that. And we have one more question to do. So the last question actually doesn't have too much related to the previous graphs. So it says, explain why the rate decreases during a reaction between sodium thiosulfate and dilute hydrochloric acid. And again, this key thing, write about particles in your answer. Whenever we see that, we should be thinking particles. Okay, we need to talk about collision theory. So to help explain this one, you need to think about what will we see if we have a graph where the x-axis is showing us the time for a reaction and the y-axis is showing us the quantity of reactant that's being used up. And whenever we plot this for a chemical reaction, we always start off with a very, very steep line. And the steep line tells us that the rate of reaction is high. And then this part here, where it's starting to level off, so the rate of reaction is slower. And then finally the horizontal part, the reaction has stopped. So this question is asking, why does the rate decrease during a reaction? Don't worry so much about sodium thiosulfate and hydrochloric acid, but why will the rate decrease during a reaction? Why does the line start to level off? And the reason is because when the reactants start to get used up, there are fewer reactant particles there, and if there are fewer reactant particles actually there, then fewer successful collisions can take place. And if you've got fewer successful collisions per second, your reaction is going to slow down. And so that's the key. As a reaction goes on, the actual number, or you could say the concentration of reactant particles, starts to decrease. And that means fewer collisions. So to get the 2 marks here,
of reactants, or if you said sodium thiosulfate and dilute hydrochloric acid, that would be fine, but the concentration of reactants decreases, and this is where our collision theory part is going to come in, and that leads to a smaller frequency, or I should say, forget smaller, a lower frequency of successful collisions. Okay, and that is the end of our exam video on rates of reaction. Thank you for watching.